So now we come to bit cell layout. And some of you had seen this layout in the DVD course, but we will go in much more detail over here. So you can tell me which one of these devices is the, so what is this device? Is this Passgate, Pulldown, Pullup? Which one is this?
It is the Passgate.
Passgate, sir.
It is Passgate. Okay. What is this device?
Pulldown.
Pulldown.
Pulldown. Okay. And we see that Passgate is smaller than Pulldown. So this is in line with what we had thought of. What about this one?
That is the Pulldown.
Okay. About this one?
Passgate.
What about this one?
Pullup.
Pullup. So this is the envelope in which they are. Huh? What about this one?
Pullup.
That is also Pullup.
Pullup, sir.
This is the Pullup. And over here, I have also cartoon way में shown that Pullup is still smaller than the Passgate. Where do you think is the word line?
Sir, it is at the Passgate poly.
It is at the Passgate poly. So in this particular cell, we will put some contacts. So what is this contact? This set of contacts?
Bit line.
They are the bit lines. They are the source node of the Passgate. Okay. What is this?
Sir, VDD.
VDD. Great. What about this one?
Sir, ground.
Ground. Great. What about this one?
Word line.
Word lines. Okay. So, and let me also put bit line over here. Okay. What is this one?
Sir, VX.
What is the name of the node? Vx is the voltage we were talking about.
BLIT.
BLTI or BLFI, one of the two internal nodes. Now, this is also the same node. And do you see this is a long contact? Have you seen such a long contact anywhere else? All of you have made layouts. Have you seen a long contact elsewhere?
No, sir.
So what is happening here?
Sir, DRC rule follow नहीं हो रहा.
DRC rule follow नहीं हो रहा. क्यों नहीं कर रहे हम DRC rule को follow?
Sir, because memory है.
तो memory है तो क्या हुआ? What, why? So if it is memory, then we will not follow DRC. We follow so many DRCs in memory.
Contact में तो area वाला DRC होता है ना, तो area वाला follow हो रहा होगा. इसे contact पे area वाला जो DRC होता है, वो वाला तो follow हो रहा होगा, मतलब इससे rectangular.
Is there an area DRC on contact?
नहीं sir.
Sir, distance between two contacts.
There is a DRC of distance between two contacts. So if I had not put this long contact over here, what do I need to do? I need to make a contact here and I need to make another contact here, and then I need to connect them. Are you able to see this? And there is a DRC spacing between these two contacts that I have to maintain. That DRC spacing, maintaining that DRC spacing would mean I have to increase the height of the memory cell. This is what I don't want to do. And to avoid that, we use these long contacts. These long contacts are used only inside the SRAM cells, not even anywhere else in the SRAM, only in the SRAM cells. Why do you think only in the SRAM cells they allow this and nowhere else?
Sir, because of symmetry.
Symmetry.
Because we
I
want
can make
to,
my sense amplifiers also symmetrical. Many analog circuits I can make symmetrical. Symmetry, so I
to
can
keep
arrange.
it compact,
Sorry.
to keep it compact.
Yeah, so I would want to make my analog circuits also compact. Why not allow it there?
I think that because we have an array kind of structure, so we know the placings already. So we can maybe arrange them because we need to anyway design the whole to custom design. So we can do that by keeping the whole structure, the array structure keep in mind. So we know every split cell, so we can then any DRC we can by custom only we can take care of that.
So what we are saying is, what Raghav over here is telling us is that, see, in fact, this memory cell would always be there in form of an array. It is not just that I want to make this one contact somewhere or this one set of contacts in some region and then remaining area is completely out of my control. When we talk of an SRAM cell, at that point of time, I know that in this pura 1000 micron square of area, this kind of pattern would appear over and over again. Because this long contact helps us in saving area very, very significantly, the process teams say that, okay, because you are using an array, you are using a systematic formation of these long contacts, we will tweak our resolution enhancement algorithms, our optical proximity correction algorithms, so that such contacts can be formed fine in an array configuration. So you cannot use long contacts independently. Long contacts are allowed only in array configuration and therefore only in memory cells. Okay. Any questions?
So in case of standard cells, we didn't know which other cell will be embedded over the one we are designing. That is why we were not using that. And now in memory, we know.
Exactly.
Okay, thank you.
Exactly.
So there is some kind of continuity in the memory, right?
I would not say continuity. Continuity you can have for SANET cells also. That is not the thing. Repetition.
Yes.
Repetition would be the better word. Okay. Repetition and
Yes.
therefore a consistent pattern. Repetition leading to a pattern through which I could optimize stuff. That is all that we are talking about. Okay. So after we make these long contacts, what do? We add the metal stubs. So first we put the metal stubs on the boundaries, and then we make these connections of the BLTI, BLFI. Okay. Now again, notice we have done a DRC violation here, just so that I can maintain sufficient, spacing between the two metals. The contacts may not be fully covered. This again is not allowed elsewhere. Nowhere else in the design can you do this. Only inside the memory cell you may have such things. Even these notches that you have, the M1 notches that we have shown here, even these notches could be violating DRC. But all this is allowed simply because we want to gain density, and it is technically possible because this is a very repetitive structure extending over hundreds of thousands of microns. Okay, so we can do something about the optical proximity correction over there. If this was not that broad and that widely used symmetrical structure, one would not want to do it. It's much risky. Okay. So because we are doing all these DRC violations, do you realize that typically memory cell yield will be worse than other logic parts? We are violating DRCs here. Are you able to see this?
So what exactly is the notches for here? This notch thing?
Okay, if you do not put this notch, what happens? Your contact is still less covered, na? Ideally, you would want to cover the entire contact. That is what your DRC says, is it not?
Yes, sir.
We have not covered the entire contact.
Okay.
We are saying instead of covering it fully, just put a small notch.
Extra
that-
metal. Okay.
It's not extra metal. It was the metal that was expected to cover the contact.
Okay.
You removed the metal from there. It is not extra metal.
Okay.
Can I ask something, sir? We are doing the DRC evaluation mainly because we want the density to be higher.
Yes, because area is diamond.
So, sir, we can do the DRC evaluations.
You cannot do. The technology team will do for you. So you will not really be designing these DRC evaluations yourself. Whichever company you join, unless you join a technology team there, unless you join the technology team that designs the memory cells, you will not be allowed to touch the layout of the memory cell at all. As a design team, you will be given this layout. But I'm preparing you for all kinds of job roles. So mostly, if you go into the design roles, you will only get a layout.
Sir,
And there are so many violations there.
Sir, you also told we can technically do because it's a repetitive structure.
Yes. Technologically, this is enabled only because it is a repetitive structure. So we know what the neighborhood is. The neighborhood is not random. So then we put the VRs. Do you see there are so many structures that are shared across memory cells? We started with the contacts here. These contacts were shared. Now these VRs are shared across two memory cells, across the cell boundary. So these are shared across two memory cells. And you see this VR, for example, is shared across 4 memory cells. Do you see a paradigm shift? When we were designing standard cells, what did we say? That whatever is the cell boundary, leave half DRC from the boundary. Hana?
Yes, sir.
Over here, we are saying do the sharing. Again, simply because we know what the neighborhood is. We know that it is repetitive. It is the same cell that is going to come repeat there. But do you see that I will not be able to, when I'm saying it is the same cell that will repeat next, I cannot really place this cell exactly translated over here. I will have to mirror it such that this is how my design will appear. This will be metal 1. There will be a poly over here. There will be this poly would extend like this. You see, we are now mirroring the cell. This mirroring of the cell is called flipping. Is also called flipping. Mirroring to hai, it's also called flipping. So you do not translate the cell, you flip the cell. So the way it is referred to is like this cell, the original cell, let us say, is called as X configuration. When I mirror it, I call that as MX configuration, mirrored X. When I look at over here, the cell over here would be mirrored on the y-axis, so it would be called as MY. And then you mirror again, and you will get Y. Okay, so you don't need to learn all this stuff or even remember all this. What I am telling you is that when we abut memory cells, because we want to do sharing, we mirror the cells, we flip the cells, so that we come into an array formation. We will just look at one of the array formations. So these are the bit lines, the word line stubs, the word line, and the ground connections. Okay. Now, do you see that in this particular layout, the word line that is running in the center has a lot of intra metal capacitance from the adjacent ground. So my word line capacitance increases very significantly. This is not what we like. So what we do is we actually cut the ground rails. And we say that we will overrun the memory cell with metal 4 rails, through which we will drop ground connections over here. Okay.
I'm not able to get this.
So in this slide, what do you see? You are getting ground from row decoder region. Are you able to see this? So see, this metal 3 that I am going to run over it is connected to this node. This node is connected to the source of the pull down. This is ground. We just discussed that. है ना?
Yes, sir.
So we are getting ground from the row decoder region. But when I do that, what happens? There are two things. First is the word line capacitance increases. This is something I don't like. If the word line capacitance increases, it will rise slowly. It will also consume more power to select a word line and so on. So this is not to my liking.
So the
So here
intermetal
we are
capacitance
talking
is
about the
increasing.
Miller capacitance.
No, this is metal capacitance, intrametal capacitance.
So
This is
intermetal.
intrametal.
Okay.
This is M3. This is also M3.
Okay. Yes.
There are 3 metal 3 lines running next to each other. There is going to be capacitance between them.
Yes, sir.
Hello?
Yes, sir.
So I don't like this capacitance. So what do we do? The only way to reduce this capacitance is cut the metal rail. But once you cut the metal rail, you still have to provide the ground connection. You provide that ground connection through a vertical metal 4 line. Instead of bringing ground from the row decoder region, you bring ground from, say IO region, vertically. Is that okay?
Yes, sir.
Similarly, you may, so over here, the VDD supply is provided in metal 2. Are you able to see this? So if you run metal 2 through the entire array, the VDD supply may see some resistance. To avoid that, you may also want to strap VDD supply, provide a metal 3 stub and a metal 4 connection somewhere at some interval, not every cell, but somewhere. Okay. So when you design the memory array, you have to take care of power routing of the memory array also very carefully. Okay. So if I just, as you're talking about putting cells in MX, MY and X, Y location, we get an array. Do you see this ground? This was the ground that is now shared with the adjacent cell. This is the word line that is shared across memory cells and so on. So we can make an array through which this sharing enables still higher density.
So from this, it seems that we have only done the kind of Y mirroring. We are mirroring vertically, right?
No, we mirrored along this axis and we mirrored along this axis also. They mirrored along both the axes. If I would not mirror along say this axis, then there will be a disconnect. I wanted to connect a bit line on the Passgate, and I need the bit line on. If I just translate it up there, there would be ground from here this side and bit line from this side.
Yes.
Not merge them. Therefore, mirroring on this side is also required.
Yes.
Okay. So any questions? Faisal?
I have one question. So
Yeah,
can
Faisal. Yeah.
So when you were talking about the yield part, so if fabrication team is allowing us to violate some DRCs, so they have prepared mask for that layout. So why there will be a yield loss in such case?
See, if they could always, if the mask preparation and this optical proximity correction was so simple, Faisal, they would have allowed everyone to use the degraded DRCs.
Yes, sir.
They allowed only you because of the repetitiveness of the structure.
Yes, sir.
But it still meant that they are pushing the limits of the technology.
Okay, due to that pushing of technology, there may be the yield loss.
There will be yield loss.
There will be the yeah. Okay. Okay, sir. Understood.
So whenever a new process node is defined, let us say I want to define the 3 nanometer process node now. The yield is actually ramped up on SRAMs. SRAM yield is determined and measured, tracked to see how the process has evolved. Because SRAMs push the technology nodes, technology limits there.
Yes, sir. Yes, sir.
Okay.
Yes, sir. Understood.
Yeah. Anything else? Deepank, you had a question?
So just confirming if metal 4 has not been shown here in this 2x2.
Yeah.
Okay.
Just because if I would show metal 4, you will not be able to see anything else. Already because of metal 3, I have put in some transparency on metal 3, but even then it's difficult to see what lies underneath. So that's why.
Sure. Thanks.
Yeah. Anything else? So in your projects, you will have to make layouts. So those of you who choose the SRAM cell project, you have to make the layouts and you have to ensure this kind of sharing is happening. Okay. In your course projects, you will not be allowed to violate DRCs, but you have to use this way of making layouts. Okay.
So we will be making this 2x2 or a single cell?
You will be making I will probably ask you to make a 64x64 array.
Okay. Okay.
Extract that. I will want you to make a 64x64 array, extract it, and then estimate the word line capacitance, bit line capacitance, etc. from that extraction.
Okay. Okay, sir.
So we will be using those long contacts, no, or we will,
No, you will be doing DRC clean only.
Okay, sir.
You do not have the, what do you say, resourcefulness to design long contacts. Not allowed.
Yes, sir.
Okay.
तो फिर हमें सर हाइट बढ़ानी पड़ेगी.
हाँ, जो भी DRC क्लीन एरिया बनेगा वो मिलेगा.
ओके.
है ना? Okay. Any further questions on this? Great. So now let us look at some other layout topologies that were either used earlier or that you may see in some books, which are no longer used anywhere today. Okay. So this kind of a topology, they've already written where the pull-up is, and can you tell me where the pull-down is? Okay, that is also written there. Where is the Passgate? These are the Passgates. So this kind of layout was used, I think, more than 20-25 years back. But many books carry only this layout for you. That is why I had to make the whole layout evolution for you. Otherwise, I would not have needed to do it. Many books would show you only this kind of layout. But please, you have done this course, do not ever make such layout in your interviews or anywhere. It is absolutely unacceptable today. Why do you think this layout is not acceptable today? Who can tell?
So lots of empty space and non-symmetrical a bit.
It is symmetrical.
They are using vias on each contact. So much vias.
We also use lots of vias and contacts. That was needed.
Maybe lots of turning.
Lots of bends. Really, look at this. This poly is bending. The direction of PMOS device and NMOS devices is different. There is a bend in the NMOS device itself. There are pull downs which are vertically, which are like this, and Passgate which is like this. Anyways, in advanced technologies, you want to keep things as simple as possible, not have any bends, nothing. So there are so many bends. यहाँ metal 1 का bend देखो, हर तरफ there are so many notches and bends. So this layout is nowhere used today, nowhere. Even if you now design in a technology which was 25 years old, you would want to use the new kind of layout that we discussed here, not this one. Okay. But yeah, over here also you will notice lots of sharing is happening. See, there's so many sharing happening here along this, because this is VDD line or ground line. So a lot of sharing happens over here also in these layouts, and you can actually make an array. But also you will see that many books, so this is taken from a book somewhere, you will see that the books have not again given you the concept of mirroring. Because they're not giving the concept of mirroring, you see they're not able to do the sharing across the cells. Are you able to see this? That was why in the beginning of the course I said no book will be able to actually give you what we are going to discuss in the class. Okay, so you will see all such stuff in the books. I'm not saying it is wrong. It is right, but it was right 25 years back. No one uses this today because this wastes enormous amount of area. Okay. However, in advanced technologies, for example, Hitachi and Renesas, they say that, see, in whatever we discussed till now, what did we say? We said that the beta ratio has to be greater than 1, so that my SNM is good. But in advanced technologies, because of optical proximity errors and corrections or whatever mismatch due to that, we see that using a regular layout, beta ratio equal to 1 actually meant a better yield. Look at this. These are the results. This is the 614, the bigger cell, which had beta ratio greater than 1. And this is the SNM. The worst case SNM is this. This is a cell with beta ratio equal to 1. Naturally, its median and mean SNM is going to be lesser than the cell with beta ratio greater than 1. Hai na? Are you able to see this still here? Hello? If I would just give you these two cells, you know that the top cell has a better SNM than the lower cell.
Sir.
Yes. You have a question?
No, sir.
Okay. So since beta ratio of the top cell is better, we know that the median SNM is going to be better, and that is what we see also. But due to mismatches in manufacturing, do you realize that the worst case SNM of this array over here is worse than the worst case SNM of the denser array? The sigma is lesser.
Yes, sir.
And that makes a very, very big difference. That is why in memories, we or this is the standard to call as, this is called as a figure of merit. So you never say median or mean value of SNM. You never quote only SNM mean value or median value. Not just that, you always also quote mu by sigma. What would mu by sigma mean? It essentially, you know what sigma is?
Standard deviation.
150.
Standard deviation. Mu is mean. When I talk of mu by sigma, what I am essentially saying is that if it was a Gaussian distributed curve, then I will go 1 sigma away. There is some probability that I am covering, one set of cells I am covering. You go 2 sigmas away, I will cover another set of cells. 3 sigma away, I will cover another set of cells. So if my mu by sigma is very large, it means my variations are more controlled. My median is very high. I do not hit a zero until far away, until very many sigmas. So if you have to quickly estimate the mu by sigma of these two cells, which one has a better mu by sigma? What is the mu by sigma over here? Something like this. 6.4 hoga. Something, yeah. What about the mu by sigma over here?
Oh, 7.4 something.
7.4 something, sir.
Okay. So even though median value is lesser, we realize the sigma value is better, and that is why the worst case cell that you see in this region, the large cell fails. It is the small cell that is better. Not only did you save area, you also had better yield finally.
So can you please focus on this mu by sigma significance? I'm not able to get exactly.
We will look at it in much more detail later also,
Okay.
when we talk about statistics linked to SRAMs. But abhi ke liye, we can look at it as the higher the mu by sigma, the farther away my mean is from zero.
Okay.
Not exactly in absolute terms, but in terms of sigma. So the small cell that is 7 sigma steps, 7.4 sigma steps away from zero, and the big cell is only 6.4 sigma steps away from zero.
Okay. And so that is more desirable the farther away it is.
Exactly, because that means that see, zero mein SNM zero ho gaya ek tarah se.
When it hits zero, okay.
And when it comes to zero,
Yes,
SNM
yes.
becomes zero. So if I'm
Yes.
more sigma steps away from zero, it means more sigma cell is covered without getting SNM to zero. So what that means is I can have more cells. So suppose mu by sigma was 1. Then do you realize only this kind of cells were functional? Other cells would have sigma equal to 0.
Yes, yes.
But if mu by sigma was 2, then I add these into functional cells. If mu by sigma was 3, even these cells become functional. So greater the mu by sigma, higher the yield.
Okay. And so, for example, looking at both these curves, so we see that the worst case of lower is better. So since we are always characterizing based on the worst case, that's why we say that the lower one is better.
Yeah, because we look at what is mu by sigma. Because mu by sigma of the lower is better, we say lower is better. Okay. Is that okay? So
but still it's counterintuitive. I think it's not trivial.
Yeah, but it is important that you understand that not everything works according to your simplistic understanding.
Yes, sir.
Are you able to see that? That simplistically, yes. See, the mean value of sigma is 154 and 190. A simple person looking at it would say the blue cell is better. Is it not?
Yes, sir.
But a SRAM designer would ask the next question: what is the sigma? A standard cell designer would not ask the sigma. SRAM designer would ask what is the sigma. We were talking about it in a little while back also, that you cannot consider designing a memory cell without looking at mismatch. You will see many papers published by many students in different colleges Just do one simulation, no Monte Carlo, nothing. And they say, I have a very dense cell. I have this kind of a cell. People in industry would never even consider reading such papers. Unless you talk about the concept of mu by sigma, unless you talk about the concept of yield or anything, all the work that is done in academia is trash, not usable. Okay.
So if my mu by sigma improves, my yield is better. So in effect, I'm beneficial. Okay, sir. Yes, sir.
So with this, we move to the next part, which is other cells.